In this video, we're going to look at an alternative derivation of the Bernoulli equation using Newton's second law applied along a streamline. So we are going to only consider two forces in this derivation. We're going to consider the forces of gravity and those forces from pressure as well. So we're going to proceed with this by doing a free body diagram of a fluid particle of size delta S, that's its dimension along the streamline, by delta N, which is the direction normal to the streamline, by delta Y, which is into the page. So we will draw our fluid particle here as a rectangle. And this is along our streamline right here. So, as we said before, this particle has dimensions of delta S by delta N by delta Y going into the page. So this is our fluid particle that we're doing a free body diagram of. I'll also make note that we have our coordinate system here, which is that we have S along the streamline and N normal to the streamline. So if we're doing our free body diagram and applying Newton's second law, then we're going to basically sum up all of our differential forces along the direction of the streamline, summation of delta F sub S, and say that that is equal to delta M, our differential mass, times the acceleration along the streamline. Well, we can rewrite this as delta M times the velocity times del V by del S is equal to rho delta V, which is our differential volume, times the velocity times del V by del S. So this is a way of rewriting the mass times the acceleration. So we're multiplying the density times the volume and then multiplying that by the acceleration along the streamline. So now we need to consider the different forces that are acting on our fluid particle. So first off, we can consider the weight force in the direction of the streamline. And we'll call that delta WS. And so the component of this acting along the streamline, we can visualize this. We have some differential weight, which we can see here, delta W. This is the weight of this particle, and of course we can break this up into two components: a normal component, delta WN, and a streamwise component, delta WS, where the angle here is theta, of course. And so this we can rewrite as minus delta W sine theta, and we can rewrite that then as minus gamma times our differential volume, delta V, sine of theta. So that's the weight force in the direction along the streamline. Now the other force that we have to deal with here are the pressure forces. So for the pressure forces, we have a pressure force acting on each face, one in the direction of the flow and one against the direction of the flow. And for each of these, we're going to use a one-term Taylor series expansion to represent the pressure here. So here we'll have P plus some differential change, del P by del S times delta S over 2, and that's going to be multiplied by the area of that face, which is delta N times delta Y. So that's a pressure times the area to give us a force. And down here, we'll have similarly P minus del P by del S times delta s over 2 multiplied by the face of that side, which is delta n times delta y. And so these are the two forces that we have to consider here. So when we add those two together, we get the net pressure force, which we'll call delta FPS, because this is the pressure force along the streamline. And so if we add those two together, so delta FPS would become equal to P minus del P by del S times delta S over 2 times delta N delta Y minus P plus del P by del S times delta S divided by 2, again, times the area of that face, delta N times delta Y. So we see what happens here is that this P cancels out with this P, and we're left with negative 2 times del P by del S times delta S over 2 times delta N delta Y, because those two terms combine with each other. And so then we can further simplify, and we find that we're left with minus del P by del S times delta N delta S delta Y. And we can say, well, we know that delta N times delta S times delta Y is just the volume of our little element there. And so we'll replace that there with delta V, our differential volume element. So we've looked at the two forces that we have, the weight force in the direction of the streamline, and the net pressure force, which is also in the direction of the streamline. And so now we can add those two together and say our net force acting in the streamwise direction is going to be, if we sum up those forces, is going to be the streamwise component of the weight force plus the pressure force. And so we can add those together, and we'll get minus gamma times the volume, delta V, this differential volume, sine of theta, minus del P by del S times delta V. So again, our volume. And we can substitute out our volume there to group terms. So minus gamma sine of theta minus del P by del S times delta V. So that is our all of the forces that are acting on our fluid element. Now we can return to our statement of Newton's second law, and we'll combine that with our statement of force is equal to mass times acceleration. And what we're going to do is we're going to divide through by this delta V term, which is present on both sides. And so when we do that, we end up with minus gamma sine of theta minus del P by del S. So again, those are all of our forces. And then on the right-hand side, we have our mass times acceleration. So we have rho V times del V by del S, which is our acceleration. So we're going to simplify this expression, and we're going to use three little tricks to do this. And we won't do this in great detail, but just to give you a flavor of how this works. The first thing that we're going to do is we're going to use a different expression for sine of theta. We're going to say sine of theta is equal to dz divided by ds, right? So we have some dz, gain in elevation, ds, distance along the streamline, and the angle between the angle of ds is theta. Secondly, we're going to use the fact that v del v by del s is also equal to 1/2 times d by ds of v squared. So those are equivalent, so we're going to substitute that in. And third, we're going to do something about this dp term. So we're going to say dp we know is equal to del P by del S times ds plus del P by del N times dN. But we're going to use the fact that dN is always equal to 0 because N is constant along a streamline. So therefore we just have dP is equal to del P by del S times ds. So we're going to substitute back into our equation, and what we'll get is minus gamma times dz by ds minus dP by ds is equal to 1/2 rho d by ds of v squared. So we'll simplify that equation and integrate. And when we do that, we end up with dP plus 1/2 rho times d of v squared plus gamma dz is equal to 0. And then we can see that that is equivalent to the integral of dP over rho plus 1/2 v squared plus gz is equal to some constant along a streamline after we integrate that. And finally, we can say that along that streamline, this is equivalent to P plus 1/2 rho v squared plus gamma z, which is constant along a streamline. And so what we have done is we have found Bernoulli's equation from a completely different physical principle, from forces equals to mass times acceleration. And of course, in class, we found the same equation from the conservation of energy. So here we have it from a completely different physical principle.